Hello, Physics 1, and welcome back after your exam. We're going to be continuing on with Chapter 8, looking at quantum states and understanding discrete energy levels. So let's look at the effect of temperature. All right, so we know that atoms can jump to higher levels if they absorb energy. So far we've talked about absorption from a kinetic energy of a particle crashing into it, absorbs some of the kinetic energy, converts that into that transition, or also photon absorption. And then of course it emits a photon by dropping down. Now, what we haven't talked about yet is the impact of thermal energy. So, in thermal equilibrium, electron levels go up and down individually, but what we are looking at is based on the average state in a collection. So whenever you've got an object like this pen, it's made of atoms. These atoms are in different energy levels. Perhaps one is in an excited state, but overall we're looking at what is the collection as a sum total. And because atoms are small and we deal with macroscopic objects, we're actually looking at a fairly large population. So one atom being excited doesn't really indicate anything about the sum total of the object. So we are looking at states based on collections, and these collections are very large. Now, when we get into talking about entropy, we will look at a few quantum objects existing of, say, 100 different atoms, where we can look at some unusual behavior, theoretically. Okay, so let's say that we've got two objects. One has a low temperature and one has a high temperature. So what you would expect to see, so for both cases, this is ground. So for the low temperature, you would expect to see that really all of the atoms would be in ground. Now, if you have a higher temperature, there is the probability that it can absorb the thermal energy and then jump up into higher levels as a result of that. So you would expect that in the higher temperature object, you would see more electrons that are in the excited state, more excited atoms. So what we are stating generally is the probability of electrons being in a certain state is related to the temperature of the material. And we can describe this relationship with the following equation. E is equal to minus E over K sub B T. So E is the energy of the ground state, which as we know is going to vary depending on the object. K sub B is the Boltzmann constant. So, which is 1.38 times 10 to the minus 23 joules per Kelvin. And T is the absolute temperature in Kelvin. So if you have it in degrees Celsius, you must convert it into Kelvin. Kelvin is really outside of the MC delta T formula. It should really be the only temperature scale that you're ever really using in physics. Okay, so, and the absolute for the Kelvin scale, 0 degrees Celsius is equal to 273.15 Kelvin. So that is what you use to convert from Celsius into Kelvin. All right, so let's do an example. So for example, if the first excited state is 1 eV above ground, at room temperature, so that would be 300 degrees Kelvin, then E to the minus E over K B T is equal to E to the minus 1.6 times 10 to the minus 19 joules. So for the Boltzmann constant that we are using, you'll notice this is in joules, so we need to have an energy that is in joules. There is an expression of the Boltzmann constant in electron volts, and you will see this if you take a Physics 3 or modern physics class. Divided by 1.38 times 10 to the minus 23 joules per Kelvin times 300 Kelvin. Now, whenever you're dealing with an exponential, you want to make sure all of the units cancel out and that your expression in the exponent is unitless, which it is. And so we get this is e to the minus 38, which is equal to 3 times 10 to the minus 17. So basically, if you have 3 times 10 to the 17 number of atoms, one of them might be excited at room temperature. So basically, this implies an insignificant fraction of atoms will excite thermally to 1 eV above ground. And so we can see then, if you were to go to the higher energy states, how much more that would drop off as a function looking at that particular temperature. So we can compare this. Oh, one other note. So therefore, it is safe to assume room temperature matter is in ground. Very safe assumption. All right, we can compare that to the sun, which has a surface temperature of approximately 5,000 degrees Kelvin. Of course, if you want to learn more about the temperature of the different layers of the sun, you can take an astronomy class. It varies where you are on the sun. But let's say, and once again, we're looking at 1 eV above ground. So then you would have e to the minus 2.3, which is equal to 0.1. So 10% of atoms would be excited that have these conditions. And that means that people who study stellar objects, that you have the potential to model some really weird states of matter because of the thermal properties of these types of objects. So for those of you that might be interested in doing astrophysics and astronomy, even something like thermodynamics is still incredibly important to a field like that. And we do a little bit of this in the astronomy class, but at a gen ed level. Still very fun. I still recommend taking the astronomy class. All right, so moving on to vibrational energy levels. So what we will see as you start to explore further is that we live in a quantum world. Nearly everything can be quantized and is quantized. And so what this chapter is doing is just giving you a beautiful little taste of this incredible quantum world that you live in, and then this will be built on in subsequent classes should you choose to progress beyond physics too. And it really, I mean, it's cool stuff. So electronic states are not the only quantized energy systems. So vibrational energy. So vibrational energy of atomic oscillations. Remember, we've been talking about all those vibrating springs are also quantized. That's right, only certain vibrational states are allowed, and you're either in that state or you're in a different state, and never in between. So, and of course, we're very familiar with the ball spring model. All right, so we're going to go quantum. Got our atoms, and they're vibrating. Okay, so for a classical system, so non-quantum, which is typically what we think about, we have seen this energy diagram before. It might have an offset, and then we're going to have various k plus u's, and really any of them are available. Be anywhere you want in here, all of these energy states. So all values are available for the non-quantum vibrational system. Also, what this also implies is that A, which is the maximum stretch or amplitude, can have any value. So energy is equal to 1/2 Ks A squared, which we've seen before. So this is the classical expression of the spring system, but we need to do a quantum update. And this works pretty well for our macroscopic systems that we've been modeling, and it could work if you were willing to make some assumptions on the atomic level. So sometimes we still use classical models because they work well enough for measurement purposes. That's always the question. Is your model sufficient for the level of accuracy that you need? Now, quantized energy was first suspected by Max Planck with black body radiation. So, which is a very interesting problem. You may cover it in some of your chemistry classes. You can cover it in some of the upper level physics classes that basically quantized energy levels solved this problem. So there's your cliffhanger. All right, and the model of vibrational quantized energy looks like this. So quantum lots of space. I can draw something really big. Get it all there. Okay, so you would have your ground state, E naught. Then you'd have your first excited state, E1 is equal to 1 h bar Ks over m plus E naught. Your second excited state, E2 is equal to 2 h bar Ks over m plus E naught. Your third excited state, and so on and so forth. Oops. And we can see, so these would be the allowed energy levels right here. And we can see that this builds upon the classical model. The classical model was necessary because it laid the groundwork for us to understand this quantum model. And to really solve it, you would need to solve Schrodinger's equations, which we won't do in this class. It's a little bit beyond this class. We would see then that delta E is equal to h bar Ks over m. So that would be the change in energy, or delta E is equal to h bar omega naught, where omega naught is equal to Ks over m. So this is the quantum update. And you'll notice, before I keep going, we have really nice equal energy spacings here. So this is different than the electronic energy models, where you had more diversity in terms of the spacing. All right, so building on these equations, let's talk about Planck's constant. So h bar is Planck's constant h divided by 2 pi. So h bar is equal to h divided by 2 pi, where h is equal to 6.6 times 10 to the minus 34 joule seconds. Notice once again we're using energy levels in joules, which means if you have energy levels in EV, you either need to convert them into joules or you would need to look up Planck's constant in EV. So, more generally speaking, the energy level for vibrational energy, En, is equal to n h bar omega naught plus E naught, where n is equal to 0, 1, 2, 3, etc., and omega naught is equal to Ks over m. So note, this starts at 0 instead of 1, unlike the electronic energy levels. So we can see this here, that when n is equal to 0, then you just have your ground state, and then it increments up, so on and so forth. Vibrational quantum energy. Great band name if you're looking for inspiration. All right, so, and as I noted before, and we'll write down, so with quantum harmonic oscillators, the spacing of energy levels is the same. Okay, so a couple other notes on quantum harmonic oscillators. So we'll QHO. Energy depends on Ks. So we still have that interatomic spring stiffness. So stiffer, K steeper, narrower potential curve with larger spacing. So like that. If you've got a smaller K, shallower, wider curve, closer spacing. Like that. And ground state E naught is not 0. And that should be obvious by looking at the pictures relative to the bottom of the well. It is 1/2 h bar Ks over m. So this is always true for E naught. It's not at the bottom. So I'll go back to this picture here. We can see this is not the bottom of the well. This is at 1/2, write that in, 1/2 h bar Ks over m. So that is what E naught equals to. So if you have h bar, you've got the interatomic spring stiffness and the mass, you can calculate the ground energy state. All right, so let's expand our knowledge of quantum systems even further and look at rotational energy levels. So we know that molecules in gas have electronic energy, vibrational energy, and rotational. So basically what you've got is you've got these molecules joined. They can be vibrating back and forth. They can be rotating. And then they can have the electronic energy levels that we've talked about with the electrons. And all of these are quantized. So we've talked about the electronic energy. We've talked about vibrational. Now we need to address rotational. And so rotational is, of course, what I just drew, like this. So this is going to have certain allowed rotational energies, E1, E0, E1, E3, etc. So allowed rotational energies are discrete. Okay. For rotational energy, all energy is kinetic. None is potential. So the rotational energies are close together And transitions tend to involve protons. Oh, sorry, photons. I thought protons looked weird. Photons on the microwave level. So that, of course, corresponds to a certain energy level of light. And what we are beginning to see is that all energies, all these quantum energies, can impact emitted photons. But there are certain photon ranges that correspond to certain energy levels. So what we saw with the electronic energy levels, we were dealing with emissions in the visible, UV, and infrared ranges. Now we're looking at energy transitions in the microwave range, which is substantially different. Okay, so moving on to other energy levels. So right now we're just doing just an overview of kind of all of these different quantum states. We can lay this really fun foundation on which to build on. And you realize that your world is not what you thought it was. So, electronic, vibrational, and rotational are not the only quantized objects. Oh no, not even by far. Nuclei and hadrons, so particles made of quarks, by the way. If you ask my 4-year-old what a hadronic particle is, on a good day she'll tell you they're particles made of quarks. I may have taught her that. I won't say she understands it. They also have discrete energy levels. And if you're really interested in this, there is a rich field of particle physics that awaits you, and it's very exciting. So nuclei have states related to the configuration of protons and neutrons. So how the protons and neutrons within the nucleus of the atom are arranged in and of themselves have allowed quantum states. And excited nuclei drop by emitting photons. So, the spacing is very large. So photon emission from nuclei are in the gamma range. So remember, that's very high energy. For hadronic particles, energy levels correspond to different arrangement of quarks. The particles that make up neutrons and protons and tauons. So you thought you were learning fundamental particles. Oh, no. It gets crazier and cooler. So these energy states are separated on the order of hundreds of MeV. All right, so let's compare all the energy spacings of what we've learned so far to just kind of wrap up our quantum discussion. And of course, all of these are concepts. We are just peering through the looking glass right now. We've not even stepped onto the other side. So if this excites you as much as it excites me, and boy does it excite me, and I don't think I'm emitting a photon anytime soon, then you have a fascinating journey of discovery in front of you in subsequent classes. All right, so hadronic states, you're looking at the orders of 10 to the 8 eV of energy spacing. Nuclear, so that would be the arrangements of, this would be the arrangements of quarks. This is the arrangements of neutrons and protons, 10 to the 6 eV. Electronic, about 1 eV. So this is the atom energy levels that you're familiar with in this class and in your chemistry classes. Vibrational, 10 to the minus 2 eV. And rotational, 10 to the minus 4 eV. And so these would correspond to atoms for electronic, and then molecules would have electronic, vibrational, and rotational. All right, so the last thing I wanted to talk about in Chapter 8 is random emission time. So this has to do with predicting the number of excited particles left after time has passed. You've seen this formula already, but I wanted to show you where it was derived from. It is a differential equation, so for those of you that are in the algebra class, you just need to know the final result. For those of you in the calculus class, it's a good idea to start understanding the equations involved with this. So we know atoms in their first excited state have a probability of when it will decay. In a time interval. And we can model this using equations. So what we're going to be looking at, here are our tools. dt is the interval of time. We want to be able to take infinite little delta t's, basically. Lambda dt is the probability of emission or de-excitation. So lambda is corresponding to how likely it is that it will decay given a particular time interval dt. Lambda is the emission rate. And naught is the atoms in the first excited state. So this is the original population. And then what we're looking for is n. Atoms still excited. After some dt. So the change in the number of atoms, n dn, is equal to minus n lambda dt. So we have dn dt is equal to minus n lambda, where the minus sign is going to indicate that this population is going to get smaller with respect to time. And so we can solve this equation. So we have dn over n is equal to minus lambda dt. So we've moved n over here, dt over here. We integrate both sides, and we end up with the natural log of n minus the natural log of n naught is equal to minus lambda t. And so we have the natural log of n is equal to the natural log n naught minus lambda t. N is equal to n naught e to the minus lambda t, where tau is equal to 1 over lambda. So we often write n is equal to e to the minus t over tau, which we have seen before. So this is the decay equation. It's probably an equation you've seen before if you've ever studied decay, but I wanted to give some context for where it came from, and you have been using this equation so far in this chapter. All right, so that wraps up part 1 of Wednesday's lecture, and we'll get ready to start chapter 9 in part 2.